So we're in section 10.5 and we're using trigonometry to find area. So we're still talking about regular polygons. That's what we've been talking about for the last few days. So just a reminder, our area of a regular polygon is always 1/2 the apothem times the perimeter. So we need our apothem, we need our perimeter to find our area. If the problem is nice and they give us the apothem and they give us the perimeter, we just need to plug into this formula. Often we'll need to find one or the other of these pieces to find our area. We talked about some special cases. We can use special right triangles. For hexagons. Equilateral triangles. And squares. Those are the only shapes that we can use our rules for special right triangles to find pieces of the little triangle that we've been drawing in the middle, the apothem or the radius, half the side length. So these are the only three regular polygons that we can use special right triangles on. So if we don't have a hexagon, an equilateral triangle, or a square, we have to use some other tools to find missing pieces of information. And that's where this idea of using trigonometry is going to come in. Because we know how to find missing pieces of right triangles with Sohcahtoa. We've spent an entire chapter doing that. So that's what we're going to do today is apply what we know about Sohcahtoa to finding pieces of our regular polygons. So let's look at an example. Nothing really new today. We're using our formula for regular polygons. We're using what we know about Sohcahtoa. We're just applying these to find the numbers to put into our formula. So we want to, for this problem, we want to find the area of the regular octagon. So let me draw a picture here. And my octagons, I know they don't come out perfect, so bear with me. Oh, it's not terrible. So there's my octagon. I know it's not perfect, but it's a regular. We're going to say that's a regular octagon. And the side length of this octagon is 7.5 inches. And we want to find the area. That's all we know is the side length. Now if this were a hexagon, we would be able to use special right triangles to find our apothem. But it's not a hexagon. So we have to use another tool. Our procedure is going to be very much the same as we did for hexagons. Let's draw in the apothem. We need to find the apothem. We need to find that. So here's my center. I'm going to draw in the apothem. And I'm going to draw in the radius. We draw this nice little right triangle inside our polygon. There's my apothem. Now when we first started talking about drawing this little triangle in here, what does the apothem do to the length of the side? What does it do to the side? Cuts it in half. So this little piece is 3.75 inches. And if I draw in a dotted line here for my central angle, what does the apothem do to that central angle? It also cuts the central angle in half. So the apothem cuts the side in half, bisects the side, and the apothem bisects the central angle. So we have a way of finding this little angle in the triangle. The angle in the triangle is half the central angle. So let's redraw this little triangle outside of the octagon, just so it's a little easier to work with. So I'm going to draw it over here. So there, just so it's a little bigger. So there is that triangle that's inside the octagon. We know that this is a 90-degree angle. There's my apothem. We know that this side is 3.75 inches. And we're going to find that angle. Well, we also talked in our very first lesson about polygons, of how we had a reminder. We did this before as well. How do we find the central angle of a polygon? It's even easier than that. 360 divided by the number of sides. So to find the central angle, we just divide the number 360 by the number of sides. So our central angle is 360 divided by 8, which is 45 degrees. The angle in the triangle is half of that. 45 degrees divided by 2, and I get 22.5 degrees. So this angle here is 22.5 degrees. I have a hard time writing that in there. Alright, so now we can use Sohcahtoa on this little triangle. So now I say, is A, for the 22.5 degree angle, is A the opposite, the adjacent, or the hypotenuse? That's the adjacent side. The 3.75, opposite or hypotenuse? Opposite. Is opposite the 22.5 degree angle? So then we go to Sohcahtoa and we say which trig ratio tells us about the opposite and the adjacent. Tangent. Tangent tells us about the opposite and the adjacent. So I write my equation. Tangent 22.5 degrees equals the opposite, 3.75, over A. And now I need to find A. Well, we spent almost an entire chapter doing this kind of thing a couple chapters ago. So now we're back to doing what we did 2 chapters ago. So to get A by itself, I want to get it out of the bottom there. So I'm going to multiply both sides by A. And those cancel. So I get A tangent 22.5 degrees equals 3.75. Divide both sides by tangent 22.5 degrees. So A equals 3.75 divided by the tangent of 22.5 degrees. Plug that into my calculator, just like that, and I get A equals 9.05. Well, now we have all of our information that we need to plug into our formula. One side is 7.5 inches. So how do I find the perimeter of my polygon? Multiply by 8. Perimeter is 7.5 times 8. 7.5 times 8 comes out to be 60 when I calculate that. My apothem is 9.05. So the area is 1/2 the apothem, 9.05, times the perimeter, 60. Plug that into my calculator, and just a reminder, multiplying by 1/2 is the same as dividing by 2, or it's the same as multiplying by 0.5. I can do this any of those ways. Plug that into my calculator, and I get the area equals 271.5 square units. So we're using the same procedure that we've used to solve all of our other problems about polygons. We needed to find the apothem. Here, because we didn't have a hexagon or an equilateral triangle or a square, we had to use trigonometry to find our apothem. Everything's the same as we've been doing before. We drew our little triangle just like we did before. We found our central angle. We talked about finding central angles. That was one of the first things we did when we started talking about polygons. And then we used Sohcahtoa to find our apothem. All right, you're good with that example. Okay, let's look at another one. It's a little bit different pieces of information here. So this one we have a pentagon. So here's my pentagon. Regular pentagon, we want to find the area, but this time we are given the length of this segment. And that is 9 inches. Is this the apothem of the pentagon? No, it's the radius. We have the radius. We need the apothem and the side. So let's draw in our apothem. There's my apothem. So this is a 90-degree angle. There's the apothem. I'm going to call this little piece of the triangle, this side X. The side of my polygon is twice that. So I need to use this triangle to find the apothem and X. So let's redraw that triangle outside of the polygon so we can make it a little bigger. So there's X, there's A, and we know that side is 9. Well, we can figure out this angle. This angle is half the central angle. Our central angle is 360 degrees divided by the number of sides. The angle in the triangle is half that. And half of 72 is 36 degrees. So this angle, coming from here, is 36 degrees. And now we can use Sohcahtoa We can use trigonometry on this triangle. So let's label the sides. Is 9 the opposite, the adjacent, or the hypotenuse? 9 is the hypotenuse. Is the apothem the opposite or the adjacent for the 36 degree angle? It's the adjacent, it's next to. And that leaves x to be the opposite. So we're going to have to use Sohcahtoa twice, once to find a and once to find x. So let's find the apothem first. So for the apothem, I'm going to say we're looking for a, so what trig ratio using Sohcahtoa tells me about the adjacent and the hypotenuse? Cosine. So I'm going to say cosine of 36 degrees equals the adjacent a over 9. I want to get a by itself, so I multiply both sides by 9. Those cancel, and I get a equals 9 cosine 36 degrees. Plug that in my calculator, and I get a equals 7.28 inches. So I have my apothem. Now let's find x. To find x, I'm going to look at this side and say which trig ratio tells me about the opposite and the hypotenuse. Sine. I'm going to say sine of 36 degrees equals x over 9. Go through the same process there. Multiply both sides by 9. I get x equals 9 sine 36 degrees. Plug that in my calculator just like that. And I get x equals 5.29. And we decided that the side of the polygon is 2x. And 2 times 5.29 gives me 10.58. Now I have all the pieces for my formula. I have the side length, I have the apothem, so I can find the perimeter. One side is 10.58, so the perimeter is 5 times that since I have a pentagon. 5 times 10.58 is 52.9. We calculated our apothem is 7.28. So now I can plug those into my formula. The area equals 1/2 7.28 times 52.9. Calculated just like this. Multiplying by 1/2 is the same as dividing by 2, so I can multiply these together, dividing by 2. Or I could turn 1/2 into 0.5 and do 0.5 times 7.28 times 52.9. Either way, I get 192.6 square inches for my area. So this is exactly like we did before with our other polygons, but because we didn't have a hexagon, we had to use Sohcahtoa to find our missing pieces. We couldn't use special right triangles here. All right, we good with that example? Again, not really doing anything new. All of this stuff is stuff that we've done before. We're just putting it together to use Sohcahtoa to find pieces, to find numbers that we need to put into our area formula. All right, last thing for this section. Area of side angle side triangles. If we have a side angle, side triangle, we can use trigonometry very, very nicely to find the area. Area of a side angle, side triangle works out kind of nice. So we'll call this triangle ABC, and we use small letters for the sides. And we're going to say that we know angle A, we know side B, and we know side C. So this little picture, you have on your graphic organizer, you have a circle for side angle, side triangles up at the 11 o'clock position. So what I would suggest is that you draw this little picture into that circle where it says the area of a side angle, side triangle, because it gives you the formula. So draw that little picture. And our area is 1/2 BC sine A. Length of this side times the length of that side times the sine of the angle between them, and we divide that by 2. And notice here that we have two sides and the included angle, the angle between them. And just like we talked about with the law of cosines, if the triangle isn't labeled the way you want it, so that your numbers don't match up with the way we wrote the formula, just label your triangle so that the angle you have is angle A, and the other two sides are, the other two angles are B and C, and that makes the two sides that you're looking for sides B and C. So you can always label the triangle the way you want. Yes? All right, so let's look at an example using this rule. This is a nice rule. Usually when you can use this one, it's very quick, it's very easy. This rule comes from the law of sines. So another little tie back to something that we talked about already. So here's my triangle. And the problem asks us to find the area. So I'm going to label the sides of this triangle. I'm going to call this angle A, angle B, and angle C. That makes this side B, that makes this side C, and I can plug my numbers straight into my formula. The area equals 1/2, 12, times 8, times the sine of 36 degrees. Plug this into my calculator, and I get that the area is about 28.2 square centimeters. So whenever we have a side angle side triangle, we just plug our numbers into this formula. It's a nice formula to be able to use. Yes?
The area, can you divide 1 by 12?
So you just multiply once. So I could do 1/2 of 12 is 6, so I could calculate that as 6 times 8 times sine of 36 degrees.
Oh, you only do 1 1?
Yes. So it's you only multiply by half once. Or you can also turn that 1/2 into 0.5. So it would be 0.5 times 12 times 8 times the sine of 36. Yes.
So here it says like half BA. We don't have A.
Oh, that's a C. 1/2 BC sine A. On your graphic organizer, that letter is a C. Just like we wrote it here, 1/2 BC sine A. So what I would do in your graphic organizer is draw this little picture, and I like to circle the angle and the two sides to remind us which parts of the triangle we're talking about. All right, we good with that example? Okay. Homework? All right, there we go.